Hello friends, myself R.D. Mazen presenting my video on partial differential equation point solution of one-dimensional heat flow equation. For that, consider a thin bar or rod of uniform cross-section area A. Therefore, that capital A is the cross-section area, unit centimeter square, of length capital L. Heat flows from higher temperature to a lower temperature. This is the direction of heat flow from higher side to lower side. The direction of heat flow is in x direction. Therefore, direction of that heat flow is in x direction only. The sides of the bar or rod are insulated so that heat cannot be radiate from it. The sides of that bar or rod are insulated by insulated material so that heat cannot be radiated from it. Length of this rod is capital L. Origin, one end of that bar is at the origin and other end of that bar is at length capital L. Then let U, which is a function of x and t, be the temperature of cross section of the bar or rod at a distance x from the origin. Therefore, this is the distance between 2 points. One is at origin and second point is at a distance L. Then the differential equation, partial differential equation, dou u by dou t is equals to c square into dou t by dou x square. This equation represents the one-dimensional heat flow equation. Therefore, dou u by dou t is equals to c square into dou t by dou x square represents one-dimensional heat flow equation through this bar or the rod, where that constant c square is equals to k divided by s into rho. Rho means density, s means specific heat, and k means thermal conductivity. We try to find the solution of that one-dimensional heat flow equation by method of separation of variable technique. For that, we call this as equation 1, given differential equation. As it is differentiated with respect to x and t's, let we consider u, which is a function of x and t, as capital X into capital T, where capital X is a function of small x and capital T as a function of small t. Then differentiating equation 2 with respect to x, keeping t constant, we get t constant outside, derivative of x is x dash. Again differentiating it with respect to x, we get t into x double dash, second order derivative. Then differentiating 2 with respect to t, differentiating 2 with respect to t, we get dou u by dou t is equals to, this time x is constant outside, derivative of t is t dash. Then substituting this in equation 1 becomes put it in equation 1. Dou u by dou t is x t dash, and that is equals to c square dou t by dou x square, value is t into x double dash. We have, after separation of variable, x double dash by x is equals to 1 by c square, t dash by t is equal to p. Equating first with last, we get x double dash by x is equals to p, and second t dash by t is equals to c square p. Then transferring this to right hand side, we get x double dash is equals to p into capital X. Then we get x double dash minus p into capital X is equals to 0. Converting in symbolic form, we get a second order differential equation. Therefore, we can write in symbolic form as d square minus p into capital X is equals to 0. Auxiliary equation is d square minus p is equals to 0. In integrating this with respect to small t, we get c square p constant term, integration of dt. Its integration is log of t as c square p t plus constant of integration small c. Then transferring log to other side, we get capital T as e raised to c square pt plus c, splitting it as e raised to c into e raised to c square p into t. E raised to c is a new constant, suppose c3, e raised to c square p t is the value of capital T. When p is negative, to suppose minus k square, then substituting that value here in this, we get d square minus of minus, it becomes plus k square is equals to 0. D square is equals to minus k square. We get d is equals to plus minus k into I, two imaginary roots, and therefore whenever we have imaginary roots, capital X is equals to, we get as roots are imaginary, we have complementary function of the solution as c1 cos of kx plus c2 sin of kx. Real part is here 0. And therefore combining these two in equation 2, we get that solution as u is equals to capital X into capital T. The value of capital X is c1 cos of kx plus c2 sin of kx multiplied by this c3 c square minus p square t as one of the solution when p is negative. Second case, when that value of p is 0, suppose, then if we put that p as 0 here, we get d square is equals to 0. Roots are 0 and 0. We get two real and equal roots for d, and therefore whenever the roots are real and repeated, that solution is given by c1 plus c2 into x and e raised to 0x, means it is c1 plus c2 x is the value of capital X, and the value of that capital T when p is 0, this becomes e raised to 0, c3 e raised to 0, and e raised to 0 is 1, therefore it is c3. Substituting these two values in equation 2, we get that solution as u is equals to x into this t, it is c1 plus c2x into c3 is the another solution when that value of p is 0. This is second case. When p is positive, that is when p is equals to k square, suppose, then that auxiliary equation becomes d square minus k square is equals to 0. It implies d square is equals to k square. We get the two values plus minus k for d. Two different values, two real and different values. And whenever we have two real and different values, capital X is given as c1 e raised to minus kx plus c2 e raised to kx, and therefore c3 e raised to c square, k square and t. And therefore that solution for you as substituting these two values in equation 2, we get c1 e raised to minus kx plus c2 e raised to kx, c3 e raised to c square k square t. This is the third possible solution. We have three different cases. When that value of p is negative, at that time we are getting the solution as u is equal to c1 cos kx plus c2 sin of kx multiplied by c3 e raised to minus c square k square t. When that value of p is 0, at that time we get the solution as u is equal to c1 plus c2x into c3. Third, when that p is positive, at that time we get u is equal to c1 e raised to minus kx plus c2 e raised to kx multiplied by c3 e raised to c square k square t. These are the three possible solutions. Out of these three, we have to consider the first one, that is as the solution of that one-dimensional heat flow equation. Therefore, we get u, which is function of x and t, as c1 cos of kx plus c2 sin of kx multiplied by c3 e raised to minus c square k square t as the solution of this equation number 1, which represents one-dimensional heat flow equation, as it satisfies the given condition. Given condition includes both boundary as well as initial conditions. Therefore, using this only, we require to find the solution of that one-dimensional heat flow equation. In my next video, I will discuss one simple problem, how we can use this to find out the solution of that one-dimensional heat flow equation. If you like my video, please share it as well as subscribe to my channel to receive the notification for my new videos. For that, you have to press the bell icon. Thank you. Thanks for